Chapter 2. Silicon Sparks, Birth of Modern AI. The story of artificial intelligence did not leap from ancient myths straight into your smartphone. Between the dream and the device, between the bronze giant Talos and the voice assistant that knows your coffee order, there was a long, winding road paved with equations, punch cards, vacuum tubes, and stubborn human brilliance. This is the story of how modern AI was born, not in a single eureka moment, but through decades of trial, error, patience, and occasional bursts of wild optimism. It is a story of machines that learn to learn, of minds made of math, and of scientists who refused to give up even when the world told them to stop. It began, officially, in the summer of 1956. A small group of researchers gathered on the campus of Dartmouth College in New Hampshire. The air was warm, the trees were green, and the ideas being discussed were hotter than anything the sun could produce. John McCarthy, a young mathematician with a quiet intensity, had sent out the invitations. He coined the term artificial intelligence for the event, a phrase that would echo through history. His goal was simple, audacious, and wildly ambitious: to explore how to make machines simulate every aspect of human intelligence. Learning, problem-solving, language, creativity, all of it. He was not alone. Marvin Minsky, already known for building one of the first neural networks, was there. Claude Shannon, the father of information theory, brought his deep understanding of signals and codes. Nathaniel Rochester, chief architect of IBM's first scientific computer, came with hardware in mind. And others, bright, curious, confident minds, all believing that human thought could be broken down into steps, into rules, into algorithms. That if you could describe intelligence precisely enough, you could build it. They thought it would take a few months, maybe a few years. They were wrong. It would take decades. But that summer in those quiet New England halls, the field of artificial intelligence was born. Not as science fiction, not as philosophy, but as a discipline with goals, methods, and measurable progress. Or so they hoped. In those early days, AI was full of promise. Programs were written that could prove mathematical theorems. One, called the Logic Theorist, developed by Alan Newell and Herbert Simon, even found a more elegant proof for a theorem in Russell and Whitehead's Principia Mathematica than the original authors had. That was 1956. Machines were not just calculating, they were reasoning. Or at least, they were mimicking reasoning well enough to impress the humans watching. Then came checkers. Arthur Samuel, an IBM engineer, built a program that could play checkers and learn from its mistakes. He called it machine learning, a term we now use constantly, but back then it was revolutionary. His program didn't just follow fixed rules. It adjusted its strategy based on experience. It got better over time. By the late 1950s, it was beating state champions, not through brute force, but through adaptation. That was the spark, the first real glimpse of what learning machines could become. But these were narrow victories. The programs worked in tightly controlled worlds, math, games, logic puzzles. The real world, that was messy, unpredictable, full of noise, ambiguity, and context. Teaching a machine to navigate that was another matter entirely. Still, optimism ran high. In 1965, Herbert Simon declared, "Machines will be capable within 20 years of doing any work a man can do." The U.S. government poured money into AI research. Corporations hired teams. Universities opened labs. The future felt close enough to touch. And then winter came. By the late 1960s and into the 1970s, progress slowed. Machines couldn't understand simple stories. They couldn't recognize objects in photographs unless the lighting and angle were perfect. They couldn't hold conversations beyond scripted replies. The early successes had been in domains where rules were clear and data was clean. But human intelligence, it didn't work that way. It was intuitive. It was contextual. It was full of shortcuts and guesses and leaps of faith. Machines had none of that. Funding dried up. Critics grew louder. The Lighthill Report in Britain in 1973 declared AI had failed to deliver on its promises. Governments pulled back. Labs closed. Researchers left the field. This was the first AI winter, a season of silence, skepticism, and stagnation. But not everyone gave up. In the shadows, work continued. A new approach emerged: expert systems. Instead of trying to build general intelligence, researchers focused on narrow domains where human expertise could be codified. If you couldn't build a machine that knew everything, maybe you could build one that knew one thing very well. The most famous was MYCIN, developed at Stanford in the early 1970s. It diagnosed bacterial infections and recommended antibiotics. It didn't just spit out answers, it explained its reasoning. Doctors could follow its logic, question its assumptions, even override its suggestions. It performed as well as, and sometimes better than, human experts. For the first time, AI wasn't just a lab experiment, it was saving lives. Other systems followed. DENDRAL helped chemists identify molecular structures. XCON configured computer systems for Digital Equipment Corporation, saving millions of dollars. These were not thinking machines in the philosophical sense, but they were intelligent tools. They proved AI could be useful, even if it wasn't conscious, even if it wasn't human. But expert systems had limits. They were brittle. They only worked within their narrow domain. Change the rules slightly and they broke. They required humans to manually encode every piece of knowledge, a slow, expensive, and ultimately unsustainable process. And they couldn't learn, not really. They could be updated but not adapt on their own. By the mid-1980s, another winter was coming. The hype had returned briefly. Corporations invested heavily in expert systems, but when the limitations became clear, the money vanished again. AI was once more out of favor, once more dismissed as a fantasy. But beneath the surface, something was changing, something quiet, something powerful. While expert systems dominated the headlines, a small group of researchers had been working on an older, stranger idea: neural networks. Inspired by the human brain, these were systems of interconnected nodes, artificial neurons, that could process information in layers. They didn't rely on hand-coded rules. They learned from data. They adjusted their own connections based on feedback. They were messy. They were unpredictable. And for a long time, they didn't work very well. In 1957, Frank Rosenblatt built the perceptron, a machine that could learn to classify simple patterns. It caused a sensation. The New York Times declared it the embryo of an electronic computer that will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. That was, to put it mildly, an overstatement. The perceptron could barely tell the difference between a triangle and a square. And in 1969, Marvin Minsky and Seymour Papert published a book, Perceptrons, that mathematically proved the limitations of these early networks. They could not solve certain basic problems, like recognizing patterns where features were not linearly separable. Their critique was correct, but it had a chilling effect. Funding for neural networks dried up. Research stalled. For more than a decade, they were considered a dead end. But not everyone listened. A few stubborn researchers, Geoffrey Hinton in Canada, Yann LeCun in France, Yoshua Bengio in Quebec, kept working. They believed the brain's architecture held the key to true machine intelligence. They tinkered. They experimented. They waited for the world to catch up. And then, 3 things happened. First, computers got faster. Much faster. What once took weeks could now be done in hours. Graphics processing units, GPUs, originally designed for video games, turned out to be perfect for the parallel computations neural networks required. Second, data exploded. The internet connected the world. Cameras, microphones, sensors, social media. Suddenly, there was more data than anyone knew what to do with. And neural networks thrived on data. The more they saw, the better they got. Third, algorithms improved. In the 1980s, the idea of backpropagation, a way for neural networks to adjust their internal weights based on errors, was rediscovered and refined. It was like giving the network a teacher, not telling it what to think, but showing it where it went wrong so it could correct itself. By 2006, Geoffrey Hinton published a paper that changed everything. He showed how to train deep neural networks with many layers, using a new technique called deep belief nets. The results were stunning. These networks could recognize handwritten digits, identify objects in images, even reconstruct corrupted data, with accuracy no previous system could match. The field had a new name, deep learning, and it had a new momentum. Yann LeCun applied these ideas to computer vision. His convolutional neural networks, CNNs, could recognize faces, street signs, animals with near-human accuracy. At Bell Labs in the 1990s, he had already built a system that could read handwritten checks. Now, with more data and more power, his methods scaled to unimaginable levels. Yoshua Bengio pushed the boundaries of language. He explored how neural networks could understand sequences, sentences, paragraphs, conversations. He laid the groundwork for machines that could not just recognize patterns, but generate them, write text, translate languages, answer questions. By 2012, the revolution was undeniable. At the ImageNet competition, a global challenge to classify millions of images, a deep learning model called AlexNet, built by Alex Krzyzewski under Hinton's supervision, crushed the competition. It reduced error rates by almost half. Overnight, the world took notice. Companies scrambled to hire anyone who understood deep learning. Universities launched new programs. Venture capital flooded in. This was not another false dawn. This was the real thing. What made deep learning different? It wasn't just power. It wasn't just data. It was the ability to learn representations to find structure in chaos. A traditional program needed humans to define what a cat looked like: pointy ears, whiskers, fur. A deep learning system, show it a million pictures of cats and it figures it out on its own. It builds its own internal model, its own understanding, not perfect, not conscious, but effective, shockingly effective. And it kept getting better. By the mid-2010s, deep learning was everywhere. Google used it to improve search results. Facebook used it to tag photos. Tesla used it to steer cars. Netflix used it to recommend movies. Siri, Alexa, Google Assistant, all powered by neural networks that could understand speech, parse meaning, generate responses. The machines were no longer just calculating. They were perceiving, they were predicting, they were creating. In 2016, DeepMind's AlphaGo defeated Lee Sedol, one of the world's greatest Go players, a game so complex that no computer was expected to master it for decades. AlphaGo didn't just win, it played moves no human had ever considered. Moves that seemed wrong until they won. It didn't just mimic human strategy, it invented its own. That was the moment many realized this was different. This wasn't just pattern matching. This was something new, something emergent. The dream of thinking machines, once confined to myth and mathematics, was now walking among us. Not as metal giants or clay servants, not as room-sized mainframes, but as silent, invisible intelligences living in the cloud, in our phones, in our homes, in our lives. The birth of modern AI was not clean. It was not linear. It was full of dead ends, winters, doubters, and dreamers. But it happened, because a few people refused to stop believing, because math met data met hardware at just the right time, because we kept asking the same question, can machines think? And kept building until the answer started to look like yes. This was only the beginning. The real transformation, the part that would shake economies, rewrite laws, challenge philosophies, and redefine what it means to be human, was still ahead. But the spark had been lit. The silicon had awakened, and nothing would ever be the same again.